all the staff members and the students in this simulation session. In this session we are going to learn about simulation of first law of thermodynamics. In the notes I have given this link. You can copy this link into your browser search box and then press enter. You will be taken to this website, or you can press Control button and then move your cursor over this link. Your cursor will be converted into a pointed finger like symbol. Then you can click on this link like this. If your computer is connected to the internet, then you will be taken to this website where the simulation is there. This is that website. So you have to scroll down to this simulation. There are many simulations. You have to scroll down to this simulation, or you can also use this simulation, that is heat capacity at constant pressure or volume. You can either use this simulation or you can use this simulation to simulate the first law of thermodynamics. So in this case, first step is you have to note down these values, or you can convert. You have to first note down these values. This is the internal energy of this system, that is 3.7 kilojoules. Temperature of this system is 300 kilojoules. Volume of this system is 200 meter cube, and the pressure of this system is 12.5 pascals. So you have to click on isobaric to ensure that this process is constant pressure, and then you have to note down these readings. These are the initial readings, which is the initial internal energy, initial temperature, initial volume, and initial pressure of the system. And then you have to click on this heat on button to heat this system, and you have to heat the system till this becomes 6 kilojoules. Okay, so this is now 6 kilojoules, right? Approximately 6 kilojoules. So you have to note down these readings, this internal energy reading, and this the final volume, that is 325.7 meter cube. Since this is isobaric process, pressure remains constant. And this temperature we don't need. You can note down, but this temperature we don't need. You only need this internal energy and the volume readings, and then you need this seconds. So now you can use these readings to find out the change in internal energy, and then work done as this. I will show you my calculations here. So I did this is the first before clicking on the heat on button. These were the readings. 3.7 kilojoules was the internal energy, and then volume was 200 meter cube, and pressure was 12.5 pascal. So this I noted down. Then when I pressed the heat on button and till I heated this system so that its internal energy becomes 6 kilojoules, it took around 7.5 seconds to increase the internal energy of the system to 6 kilojoules. While increasing this internal energy to 6 kilojoules, its volume increased to 320.3 meter cube. Since it is an isobaric process, the pressure remained constant at 12.5 pascals. And since this heat source is, the heat source is here, it is 500 watts, that is 500 joules per second. So heat source is 500 joules per second. So you can find you can find the heat supplied using this formula. That is, you can see here 12.5 heat. Okay, so the time taken to heat the system is 7.5 seconds. The heat supplied during these 7.5 seconds are 500 joules per second, which is fixed, into 7.5 seconds. Seconds get cancelled. You got only joules. So if you multiply these things, it will be 3,750 joules. This much heat you are supplied during 7.5 seconds of heating of the system. Then the internal energy of the system has increased. What is that change in internal energy? This is du. The initial internal energy was 3.7. You can see here in this picture. You can see the initial internal energy was 3.7, and when the heating was stopped, the internal energy was 6 kilojoules. So if you have to take the difference between these two, you will get 2.3 kilojoules, which is 2,300 joules. And you can find out the work done using this formula. Since the pressure is kept constant, P into V2 minus V1, P is 12.5. V2 is the final volume when the heating stopped is 320.3 meter cube. That I have used here. The initial volume before heating was 200 meter cube. That I used here. I subtracted between 320.3 and 200. What you got is, it is 1503.75, 1503.75 joules was the work done. Now you have to get this sum of the work done, dW, and the internal energy. The sum of dW and du, that is the change in work done and the change in internal energy, are 3803.75 joules. The heat supplied is around 3750 joules. So now it is approximately the left hand side, as per the first law of thermodynamics, dq is equal to du plus dw. So that is the first law of thermodynamics. Since the sum of dW and du is 3803.75 joules, and the heat supplied is 3750 joules, which is approximately equal to this value. Hence, we can say that the first law of thermodynamics is there, which is true. Hence, we have proved that we have proved the first law of thermodynamics. Thank you.